Hi, my name is John Lenchner, and I'm with IBM Research in Yorktown Heights, New York. And this is joint work with colleague Ellie Packer from Intel in Haifa, Israel. The title of this talk is Line Segment Visibility, Theoretical and Experimental Results. So the motivation for this work is the need to do thermal monitoring in commercial data centers. We need to measure the temperature on all relevant surfaces to detect emerging hotspots. So we either monitor most often monitor the air intake of servers and sometimes also the exhaust side of servers. And in this study, we are deploying infrared cameras to see these surfaces. They're temperature sensing cameras. And the problem is that the cameras are expensive, so you want to deploy a minimal number while seeing all the surfaces. And so there's a certain analogy to art gallery problems. In our model, we model the racks of equipment as line segments inside a bounding rectangle. So data centers are typically approximately rectangular. We assume the segments don't intersect one another and they don't touch the bounding rectangle. We model the guards as point cameras with a full 360 degrees visibility, not a perfect model, but the one we adopt nonetheless. And then there are two models of segment orientation. One is where all the segments are vertically oriented and another where the segments are axis aligned. And there are three different guarding models, the first of which we call solver's choice. So given a set of line segments, the solver gets to choose which side to guard. So this is analogous to a case where you come into a data center, you can reorient the equipment to make it easier to monitor. And in the illustration below, an optimal choice is the segment sides indicated with the red ticky marks, which allow us to use one camera or one guard to see every consecutive set of three segments. Second model is what we call poser's choice. So in this instance, the problem poser tells us which sides of the segments we must see. And so in the same set of segments, the poser might dictate that we see the indicated sides. And in this case, n/2 guards or cameras are required. And in the third model, we have to guard both sides. So this is analogous to being required to monitor both the intake and the exhaust sides of the equipment. Then within the solver's choice and poser's choice models, there are two submodels. A first model for solver's choice where we can see some points from one side, some from another, and a second, more practical model where we need to guard all points of a segment from the same side. And then for poser's choice, either the poser has full reign of telling us what sides of the segments to guard, or they must tell us a consistent orientation. So for example, all vertical segments from the left and all horizontal segments from the top. And then there's a third model that cuts through all the examples, and that is so-called all but delta model, where the poser comes up with a very small number delta, and he tells us that he's satisfied to see, for us to monitor all but this very small distance, say a few inches along any segment. And if we look at the example illustrated, where the sides we need to see are given in red, we can actually see each of the segments in each of these H regions with one camera, if we're allowed to omit a small delta. Now you'll notice that this camera, while it sees the right segment and the middle segment in each packet of three, there's a small segment along the left edge that's in the shadow of the horizontal segment, but that unseen segment can be made arbitrarily small by sliding the camera down to approach to where the horizontal segment is. If, on the other hand, we were required to see all segments in full, we'd have to deploy two cameras for each of these H's, and so would be required to see use 2n/3 cameras in total. So our program is then to devise art gallery theorems, in other words, find upper and lower bounds so that we can see all segments in the worst case. Then another part of our program is to prove NP hardness results, something that we do in our paper, but I won't go over here. And once we've proven that finding exact solutions is NP hard, we then try to find approximations, typically constant factor approximations, although for the vast majority of art gallery problems, this is and this variant as well has proven very hard. Failing that, we develop algorithms or heuristics for guarding, and then in our case, we're going to run experiments to simulate these algorithms in large real-world data centers, and simulated data centers. So these two tables summarize what we know about the combinatorial bounds for all the problem variants mentioned, solvers, posers, choice, or both side guarding, and then the orientations, vertical or axis aligned, what we call here orthogonal orientation, and then for the two cross-cutting cases of complete coverage and all but delta coverage. And you can see that in the vertical case, the upper and lower bounds are tight, so we have solved those problems combinatorially completely. But in the case of axis-aligned orientation, there's only one case for the complete coverage and two for the all but delta coverage where these bounds are tight, and so there's a lot of work yet to be done. And there's some prior work done by Sisovich et al. For the solver's, one of the solver's choice variants, and also for from Shabatoth, who actually showed us the example that I illustrated on the last slide that requires 2n/3 for guarding every point and n/3 if we're willing to overlook a small delta. And he's also responsible for the upper bound in both sides guarding of 4n/5. Okay, so going back to that example, we pointed out that 2n/3 are required if you want to see all points of all segments from the poser's choice of sides, and n/3 for all but delta. But in fact, we have a better lower bound than that n/2, and we've already seen it. Here's an illustration of a poser's choice instance that requires n/2 guards. Okay, so let's now veer from considering the combinatorial bounds to problems involving practical heuristics. Again, I've said that we've not, to this point, not been able to find any constant factor approximations for this problem. But in these practical heuristics, rather than considering line segments, we consider the more general problem of rectangles with marked sides that need to be guarded, so a more faithful model. And typically, the rectangles have one long side and one narrow side, in keeping with the dimensions of the racks. And we mark the sides or the edges of the rectangle in keeping with the respective models of solver's choice, poser's choice, or both side guarding. And one of the interesting things to point out is that the most common heuristic used for guarding these types of problems, which are really polygon with hole problems, in the literature doesn't work so well for a whole family of instances of the problem that we're considering. And I want to show you why now. So first, let me tell you what that heuristic is. I'm going to illustrate it with these well, very thin rectangles. They actually look like thick segments. Either way, it doesn't really matter. So the heuristic starts by extending these very thin rectangles or segments so that they touch a neighboring one or the rectangular boundary. We do that with every single segment. And it induces a rectangular subdivision of the boundary rectangle. And within each of the induced cells, we place a candidate guard, and that gives us a integer program. We then, where the candidates either can be chosen or not chosen, and the idea is to choose a minimum set that actually guards all the segments. And it's obvious that if we start with a candidate in each, or a guard in each of the cells, the guards in total see all the segments. But actually, this heuristic turns out to fare quite poorly in these cases that have what we call an abutting property, where the segments have already been extended to come up very close to the one another or the boundary. So in this very simple example of n, we've actually seen it already, n segments, vertical segments, and in this case, we're requiring that they all be seen from the left side. So again, just like a prior instance, we can see these segments with n/2 guards positioned as you see with the red dots. But if we apply the prior heuristic, it leads to a rectangular subdivision, as you see below, and placing candidate guards at the center of every cell, we see that the ideal candidate location doesn't come up. And from such a set of candidates, the best we can do, we actually have to pick one of the candidates from each of the vertical columns, one of the two. And we're going to end up, no matter what we do, with n cameras seeing the n segments. And so we do twice as worse, quite a lot worse than optimal using this heuristic. So instead what we do is we just do a much sort of take a much more naive approach, and we create a square mesh, a uniform square mesh that covers everything but the holes. In other words, these little or thin rectangles. And we just try to get more and more. We start out with a coarse mesh, and we go to finer and finer meshes. And the idea is that at some point, the solution should plateau at what is the optimal solution, or near optimal solution. There are two issues, however. First, it's important to do a pre-processing step where we break each segment up into subsegments so that the candidates all see segments entirely or not at all, because the heuristic doesn't work for teamed up or shared guarding. Okay, the second thing, well, there's a minor point that I'm just going to gloss over quickly, is that we prefer segments with high quality, but not at the expense of using more cameras in total. So we favor cameras, all things being equal, that see segments at not too steep of an angle or at too great a distance. And it leads to an IP that looks like this. The key parts of the equation are here. The vector C is a vector of which candidates are selected. So it's a long column vector. 1 means the candidate is selected, 0 that it's not selected. M is the visibility matrix. The ijth entry corresponds to whether segment I is seen by candidate J. Okay, and the idea, well, one of the problems is as we get to finer and finer meshes, more and more candidates need to be chosen from. And so this becomes a bigger and bigger IP, and we can't solve it on using today's methods. And so what we do is we naively just relax the problem to a linear program, and then take the candidates with the highest yes, we relax it, first of all, to a linear program where the candidates now can be chosen not from just 0 and 1, but from the closed interval 0, 1. And then the candidates with the highest assigned values, we round up their values sequentially to 1, and then track how much of the segments we're able to see with so many guards. Once we see everything, we stop, and we take those candidates. Leads to a slightly inferior solution, but as you'll see, not bad. Okay, so here's some illustrations of some of our experiments. Did it on a 1,000 by 1,000 grid, simulating a 1,000,000 square foot data center, 1,000 feet on an edge. And we experimented with 50 up to 300 rectangles or racks per experiment. And the little red points in each of these squares correspond to the found guard set. And plotting the number of guards versus the number of racks, we get an approximately linear curve. Although, if you look closely, well, one thing to notice, we used a 1,000 second threshold. So after running the IP for 1,000 seconds, we then gave up and reverted to the LP. And you can see that the actually line is slightly it's piecewise continuous, but basically it has a line of this slightly lighter slope. That's for the IP, and then the slope becomes just a little bit more steep, indicating that the LP gives slightly worse solutions than the IP. And there's approximately 10 guards needed. I mean, 1 guard needed for every 10 racks. So future directions, of course, we want to tighten up our combinatorial bounds, try to find constant factor approximations, though this is likely to be very difficult. I've shown you experimental results actually just for the poser's choice variant of the problem. We want to do the same for the solver's choice. Also, we want to experiment with the all by delta variant of the problem and understand the sensitivity of that parameter delta with regard to the number of needed cameras. And then also get theoretical bounds for more realistic camera models, where the cameras can only see a more restricted angle, have a more restricted angle of visibility. So with that, thank you.